question, though, is how do we harness this? I don't think anybody wants this to happen in their cell phone, especially when it's in their pocket. So how do we actually control this so that we can let that 4 volts out slowly and take advantage of it and actually use it to do something? To do that, we separate the two reactions. So for instance, I could put the sodium on one side of something and then the chlorine on the other side. And as long as I connect them and allow electrons to go from one side to the other, which I would have through this wire, by changing the size of the resistor here, I can control, just like a valve on a faucet, how quickly the electrons go from one side to the other. And so I can slow that reaction down if I want by letting fewer electrons through. I can open the valve and let more electrons through and let the reaction go faster. Or, what's even better, is I can put something here that uses those electrons to do work, because the electrons want to go from one side to the other. And so that is, in essence, a battery, where we take two reactions and take the electrons out of them and make it go through an external circuit. So what are the important things about batteries? What are the important numbers that we have to keep in mind or try to improve on? So one of the biggest things, especially if we want to use these in cars, is the weight. If a battery is too heavy, it's not going to be good for cars. We also have to worry about the size. No one wants to drive ginormous tanker trucks around just because you have to have a large battery. How much energy they store, how quickly they can deliver that energy. So if it takes too long to charge your battery, for instance, no one wants that. And also how much they cost. And so the ideal battery has a few different things. It's going to be very light, it's going to be very small, it's going to have a very high voltage, it's also going to be able to have a very high current, and it's going to be very cheap. And so, kind of where are we right now in batteries? Again, to know where we want to go, we have to understand where we are. In cars, and I'm focusing primarily on cars just because I wanted to have some focus on batteries, and cars are as good as anything. There are 3 types of batteries used in cars. The first of those is lead acid. This is the kind of the type of battery that everyone has in their car. It's used to start the car. The second type are nickel metal hydride batteries, and the final type are lithium ion batteries. And so I'm going to talk about each of these real quickly. We're going to skip that. We're just going to go right here. There's one very serious problem with batteries, though. If I were to take the absolute best, most highest energy storing battery I can imagine, even on paper, even if I can't build it, just the best one I can imagine in my mind, and I compare it to things like gasoline, how does it compare? It turns out it compares horribly. So, for instance, well, maybe not horribly. Currently, it's horrible. So this would be down in the very corner near 0. This would be the best lithium-ion battery on the market today. Gasoline is right here. And so what this is a comparison of is how much energy in terms of volume and in terms of weight. So something up here would be extremely light, extremely small, and have a lot of energy. So you can see that gasoline does very well. It is very light, it is very small, and it delivers a lot of energy. Lithium-ion batteries, on the other hand, the type of batteries you have in cell phones and computers, not so much. In terms of how much it weighs and how large it is, it's horrible at storing energy. In the future, we're hoping to get to about here, where I just have lithium, or better yet, aluminum, which stores a lot of energy for how light it is. So batteries based on aluminum would be extremely light and fairly small. Batteries based on just lithium would be very light, but a little bit bigger for how much energy they store. And so let's talk about the current technology first. So I'm not going to worry about the lead acid batteries. They're really not that good. They're horrible. They wouldn't even be on that chart. The 2 that we currently have, at least for cars, is this nickel metal hydride. These are okay batteries. They're the types of batteries you'll find in a Prius, for instance. Unfortunately, these numbers, so how much energy it stores in terms of its weight and its size, isn't good enough to have a battery-powered vehicle. They're only useful really for hybrid vehicles. So vehicles that use the battery sometimes, but not all the time. Lithium-ion batteries, on the other hand, are a little bit better. They store enough energy for something like an electric vehicle, but the problem is that they don't have enough current. you can't get the energy out of a lithium-ion battery fast enough, at least currently, in most cases, to make them useful for cars. This has changed in the last couple of years a little bit, but lithium-ion batteries at least do have the potential, if we can get the current better, to power full electric vehicles. And there are some examples of full electric vehicles based on lithium-ion batteries. So what I'm showing here is the Tesla Roadster. And the Tesla Roadster looks really cool. It has very good performance capabilities. It's got a rather large lithium-ion battery. On a single charge, it can go about 250 miles. Unfortunately, it takes about 3.5 hours to recharge the battery. So if you're driving cross country and you make it 250 miles, you're going to have to sit at the gas station for 3 hours instead of 3 minutes to fill up with gas. And that's one of the biggest problems with batteries in general. However, in terms of its efficiency, it's extremely efficient. So if it can get about 28 miles per dollar, because it doesn't use gallons of gasoline, and electricity ends up being much cheaper than gasoline. So it can go about 28 miles per dollar, whereas my Honda Accord, which is fairly fuel efficient, is about a third of that. It can only go about 10 miles per gallon, or I'm sorry, 10 miles per dollar. And I did this calculation before the fuel prices jumped in the last couple of months. So the other problem with this, well, two really, this is awesome, but it's going to cost you 100 grand. And I don't know too many people that have 100 grand lying around to put a car in their garage. The other problem is with this battery itself. This battery is the majority of this cost. These batteries are extremely, extremely expensive. This battery in the Tesla Roadster has to be replaced every 5 years or so because it just wears out, at the cost of about $30,000 to replace the battery. So that's buying a new Honda Accord every 5 years. I don't know too many people that can do that either. Although, if you can do this, I guess you can afford a Honda Accord every 5 years too.
Is there any way you actually go to a gas station, instead of charging your battery, actually change a new battery?
That's one of the things that people are talking about doing. Yeah, yeah. Okay, so what's next? Now that we know where we are, what needs to be improved? Well, a few things. One, this charge time. No one wants to sit at the gas station for 3.5 hours. It's certainly possible to, as Lynn mentioned before, switch out batteries or switch out parts of batteries, and that would go much faster. But even so, trying to get people to figure this out ends up being difficult. The range. So this Tesla Roadster, which is state-of-the-art, can go about 250 miles after a full charge. My Honda Accord can go about 400 on filling up the tank of gas. So we need to increase how far these cars can go. The power. In a Tesla Roadster, they have pretty good power, but to do that, they have to make the batteries even more expensive than they normally would be, and the batteries wear out quite a bit faster than they would if you didn't have to discharge them as fast. And so getting higher current batteries is extremely important, especially for things like cars, because people like to drive aggressively. At least I do. Most people I know do. No one likes going exactly the speed limit for hundreds and hundreds of miles and never passing anyone. And then finally, the cost. No one wants, well, very few people want to buy a $100,000 car. That's not true. Very few people can afford to buy a $100,000 car. I would love to buy a $100,000 car, just can't afford it. And so there are kind of three different ways that we're going with this. The first is to make the electrodes better. And by better, that so far has meant going into nanostructured materials. Finding alternative chemistry. So for instance, I mentioned earlier that aluminum would be excellent, but really there aren't too many people working on aluminum. And then finally, electrolytes. So the actual thing that is keeping the battery from going fast is what's allowing the charge to move in the battery, not outside of the battery. Okay. So why do we want to move to nanomaterials? There are two reasons, really. One is for safety. Turns out that nanomaterials, or batteries based on nanomaterials, tend to be safer. They don't, if you were to puncture a battery, it won't catch on fire like some Sony batteries will back a few years ago. The other nice thing about nanoparticles is because they have a much higher surface area, we can get the charge in and out faster. And that means that we can charge and discharge the batteries faster. So as an example of this, what I'm showing here is a motorcycle. This is an all-electric motorcycle that uses batteries with nanoparticles as its basis or its energy storage. And so it's unfortunate that I don't have sound, because the sound is kind of cool too. It actually sounds like a gas golf cart. And it doesn't sound at all like a motorcycle. And this was a few years ago at a drag strip. And you can see that it can put out a lot of power, right? Here we'll see it's going about 155 miles an hour at its fastest point. Went a quarter of a mile in about 8.5 seconds. That's pretty good. That's pretty good for a normal motorcycle. And so these batteries at least have the potential to discharge very quickly. Otherwise, it wouldn't be able to do this. Again, unfortunately, it becomes very expensive. And most of this is not ready yet to be manufactured. It's still in its research stage. Another useful material, turns out, is silicon. Again, we come back to silicon, but nanostructured silicon in lithium-ion batteries ends up being extremely, extremely useful. It can store a lot of charge, and so that means it can store a lot of energy. Turns out that silicon can actually store more lithium than lithium metal can, which sounds weird, but in terms of how much it can store per unit weight, silicon stores more than lithium. So a battery based on silicon and this lithium iron phosphate that I had just talked about, if it's all nanostructured, has the potential to store a lot of energy. Unfortunately, this is all very new. This is only in the last 2 to 3 years that people have really started to figure out how to do this. The problem is that even though silicon stores a lot of energy, as we charge and discharge it, the silicon breaks because it's brittle. So people have tried to find ways around this, and one of the ways they've come up with are using nanowires instead of just pieces of silicon. Another very useful, very new type of battery are what are known as lithium-air batteries. And so, as I mentioned before, all batteries have two materials, something that really wants electrons and something that really wants to take electrons, or give up electrons. And so in lithium, for instance, the thing that's giving up the electrons is lithium. The thing that wants the electrons is usually some metal, like iron or iron oxide. Here, people have come up with a slightly different way of doing this. They still have the lithium to give up the electrons, but the thing that wants the electrons in this case is just air, so just the oxygen in the air. It turns out oxygen in the air really wants electrons. And so by doing this, by using air as one of the components of the battery, they can make batteries that are very light and store a lot of energy. In fact, these batteries, in terms of their energy density, are very close to gasoline for how much energy they can store. The problem, though, is two. Two problems. One, these tend to be very unsafe because you have metallic lithium, and so they tend to catch on fire if you use them. The other problem is that, at least so far, people haven't been able to make these rechargeable, at least for very many cycles. So these make okay primary batteries, but not useful for cars because you can't recharge them. And so, kind of in conclusion, since I'm pretty much out of time, is talked about a few things. Talked a little bit about solar energy, why we might want to use solar, but what are the problems with it, right? We have this huge excess of energy coming from the sun. How can we harness that? But how do we do that in a way that's cost efficient, cost effective, and how do we store that energy? Talked a little bit about how solar cells work using semiconductors or some of these alternative materials such as organic semiconductors or organic dyes. How we can address the cost of solar cells. Solar cells, at least currently, are way too expensive for most use. So how can we address that? So talked a little bit about research going on at least around this country, on new materials, new types of manufacturing, new types of solar cells, just based on a variety of different ideas people have had. And then a little bit on batteries and how we can store this electricity that solar cells produce. Use it at times that maybe the sun isn't shining. And so thank you very much for your attention.
Wow.